Welcome back, students. In this video segment, we will cover section 12.5, equations of lines and planes. Equations of lines and planes. So let's start this, this video segment by looking back a little ways. Let's take a look back at something we did a lot of in algebra. The question is, how do we find the equation of a line in R2? So how do we find an equation of a line in the xy plane? After so many semesters of calculus and pre-calc and algebra, this should be pretty automatic for you. As long as the line is not vertical, the answer might be given. Let's do this. Given a point, let's say x sub 0, y sub 0, and a slope, let's say m, then the answer, the equation, or an equation, can be found very, very quickly by using the point-slope form of a line. It would look like y minus y naught, or y sub 0 equals m times x minus x sub 0, or x naught. Okay, so I want to rephrase this question by just changing one thing. So the new question is, how about in R3? Okay, so I'm being a little lazy here. Instead of writing out the entire question, the question is, how do we find an equation of a line in R3? Well, we can still be given a point. In fact, that's very common. So we're given a point, and the point might be x naught, y naught, z naught. There's no such thing as this concept of a slope, which is rise over run, going into lines for R3 though. So what do we replace the concept of a slope, rise over run, with in Calc 3? Well, if you look back at the line in Calc 2, sorry, not in Calc 2, but in algebra, here's a little red line. If the slope were, say, let's see, how do we want to do this? If the slope were, say, m equals b over a, then we could look at it, at the geometry, as a is your run and b is your rise, and we could replace that slope with a vector. We could replace that slope with the vector that I'm positioning along the hypotenuse of that little right triangle. And we could identify that vector as, say, v, and the vector v is defined as, in Calc 3, as a direction vector. So we could give, instead of the slope, we could give the direction vector in terms of its components, a and b. Now that's how we're going to do this in R3. Since we don't have a concept of rise over run for Calc 3, at least yet, we're going to have a sort of generalized concept of slope coming up when in chapter 14, I believe it is. But for right now, we don't have a concept of slope. So instead, we're going to replace the idea of the steepness of a line being given by its slope with the steepness of a line given by a direction vector, an arrow that points in the direction of the line. So instead of the slope, we're going to be given a direction vector. Let's say direction vector v, whose components are, say, a, b, and c in R3. Okay, so let's take a look at what this looks like geometrically. So we can start out by taking a look at, or letting, let's say, let r naught, or r sub 0, be the position vector to our point x naught, y naught, z naught. Okay, so let me actually draw that in here. So here's r naught as a position vector. Okay, that'll work. Kind of need a little arrow at the end of r naught though. Okay, let's see here. Well, there is a little arrow there, but I want to make it a little bigger. Okay, so here's r naught, and that r naught points right at, the tip of that is right at the point x naught, y naught, z naught. And let's say we sketch the graph of the direction vector, let's say in red. Let's do that. Here's our direction vector in red. So I can get the arrow to show up a little bigger. That's good enough. So here's our line. Our line goes through the point x naught, y naught, z naught, or through the tip of our position vector, and points in the direction, or goes in the direction of the red vector. So the red vector is our direction vector. So here's our goal, is to find an equation for that line. Okay, again, the little red vector is the direction vector v. Okay, so I'm going to start this by finding an equation for one specific vector. I'm going to draw the vector. I want to find an equation of the vector that goes from the origin to the tip of v, if my surface will allow me to do it. Let's see, from the origin to the tip of v. And I think I'd like that to be in black. Okay, so I'd like that vector right there. Now, keep in mind that the initial position vector is r naught. So what is an expression for that vector that points from the origin to the tip of v? That vector is given by the sum of the two vectors, r naught plus v. So r, which is r naught plus v, is a position vector of one point on the line. Now, suppose that I take r naught and add 2v, and I'm going to look at what that resultant vector looks like. Well, in order to do that, I'm going to need some more room in my graph. So let's, instead of right on top of v that's pictured in our graph, let's draw 2v. 2v, the vector 2v will be, let's see if I can do it, change the color here, and if it won't mess things up too much. I'm going to draw 2v with green. So 2v will go from r naught, oops, I lost my line, will go from r naught and stretch out 2v in distance. Yeah, I'm going to have to fix that off camera here. So I've cleaned up my graph a little bit. So there's 2v pictured. So r naught plus 2v will be the following vector. R naught plus 2v then will be from the origin to the tip of where 2v is. Let me redraw that. Here we go. This should work. And I'll make the arrow a little stronger. And the tip of that vector is on the line. So what if I had R naught minus V, okay, which is the same thing as R naught plus the opposite of V. Well, I think I ought to change colors for this now. Okay, so at the point x naught, y naught, z naught, I'm going to draw the vector downward of negative v. Then, that's a terrible looking vector, the vector r naught plus the opposite of v is then the vector from the origin to the tip of the green vector. The tip of that green vector looks terrible. Okay, it doesn't look much better. So r naught plus negative v is on the line. So as we consider adding r naught plus different multiples of v, we trace out the line. So all these vectors, r equals r naught plus v, r naught plus 2v, r naught minus v, these are all vectors that lie on the line. So it seems reasonable to expect that r equals r naught plus any multiple t of the direction vector b will be on the line. All of these position vectors, r equals r naught plus tv, will be on the line for different values of t. The simplest is when t equals 0, you get r equals r naught, the initial position vector. This is in fact the equation of, or what's called the vector equation of a line. This is what's called the vector equation of a line. So let's take a look at a specific example. So for example, I want to find the vector equation. Find the vector equation of the line that passes through the point -3, 0, 4, parallel to the vector v equals -1, the vector whose components are -1, 3, and 2. Okay, so I'm given a position vector. I'm given a position vector in the form of a point. So our position vector is r naught equals -3, 0, 4 now as a vector. So our line, the vector form of line is r equals r naught plus t times the direction vector v, or r equals -3, 0, 4 plus t times the vector -1, 3, 2. Okay, and that's the vector equation of this line. Okay, now we need to look at other forms of equations of lines in 3 space. So what I'm going to do, just to keep things sort of identified here, I'm going to underline the vector equation of a line. This is our first equation of a line. And then we're going to look at other forms of equations of lines. Okay, so let's do that right now. Let's take a look at other forms of lines. So let's take a look at taking the vector equation of a line and writing the equation component-wise. If that didn't make sense, I'm just going to do it for you here. Here's the vector equation of a line. R equals initial position vector plus t times the direction vector. Now let's replace these with specific vectors. So let's say x, y, z, the vector whose components are x, y, and z, are vectors, are position vectors on the line. The initial position vector is x naught, y naught, z naught, plus t times, and let's say the direction vector is a, b, c. So there's the vector form of the line, vector equation of a line, written with all the components intact. Now let's simplify the right-hand side, or perform the actual addition on the right-hand side. So we get x, y, the vector whose components are x, y, z, equals x naught plus a times t, y naught plus b times t, and z naught plus c times t. Okay, so those are the individual components of the vector, of the points on the line, the vector that gives the points on the line. Now let's just isolate the components. So x must equal x naught plus at, y must equal y naught plus bt, and finally z should equal z naught plus ct. These three equations together, they give the equation of the line. They give the actual line. These are called parametric equations of the line. Parametric equations of the line. Okay, let me write that out. Okay, so I think I'll do that in red. When you consider all the equations together, these are called parametric equations of a line. Okay, so notice there's no vectors. There are no vectors in this representation. We just have three separate equations. And the value t varies through all real numbers. It's convenient to view the variable t as representing time. So at time equals 0, the line, or the point on the line, is x naught, y naught, z naught. So when time equals, let's say 1 second or 1 hour or whatever unit of time you're measuring, the new x value is the old x value plus a, new y value is y naught plus b, z naught plus c is the new z value. So as t varies through all real numbers, or as time varies, we pick up different points on the line. Okay, and it's okay for time to be negative. It's a very common convention to use time equals 0 as a starting point, but there's nothing wrong with time being negative. Okay, if we didn't allow time to be negative, then we wouldn't be able to consider, let's say, the Big Bang relative to time equals 0 here on Earth. So the Big Bang was t equals something like negative 14 point something billion years ago. Okay, so t, it's convenient to represent t, at least mathematically or physically, as representing time. It gives us a way to think about how this line is formed. So let's take a look at a specific example using parametric equations. So for example, find parametric equations. Find parametric equations of the line, let's say passing through the point -3, that's a terrible -3, -3, 0, 4, parallel to the vector -1, whose components are -1, 3, and 2. Okay, so again, I do believe we are looking at the exact same data that were given before, but we want a different form. We want a different form of this line. So x will equal your initial x value, x naught, plus at. Well, a is -1, so minus t. Y equals y naught, 0, plus 3t, so y equals 3t, and z equals your initial z value, 4, plus c, the third component of your direction vector, times t. And these three equations, all taken together, they give you parametric equations of a line. This is how you identify a line. One way to identify a line in 3-space. Or 2-space. In 2-space, we wouldn't have the z component. So we can also consider this method of writing equations of lines in 3-space. We could carry this over to the special case in 2-space. Okay. Let's take a look at another example. So for another example, find parametric equations. Parametric equations of the line. Let's say passing through P1, let's say 1, 2, 3. So we're given 1 point on the line. And P2 equals, not a real exciting second point, 4, 5, 6, just to keep the coordinates simple. Okay. Well, what do we need for a line? We need two things. If it were a line in R2, we'd need a point and a slope. It's a line in R3, so we need a point, and what is it called? A direction. So for the point, we could either choose 1, 2, 3, or 4, 5, 6, so it makes no difference whatsoever. And instead of a slope, we have a direction vector. Direction vector. How can I find the direction vector? Well, look off to the side here. If this red line is our line in question, and if this is the point P1 on the line, and this is the other point P2, I want the displacement vector P1, P2. The displacement vector P1, P2 is what I'm going to choose to be my direction vector. So I'm going to choose as my direction vector V to be the vector P1, P2. And the displacement vectors are super easy to find. To find the components, you simply take the difference of the components of P2 and subtract the components of P1 in order. So 4 minus 1 is 3, 5 take away 2 is also 3, and 6 take away 3 is also 3. Not real original. Okay, so the solution is x equals x naught, 1, plus at, 3t, so y equals 2 plus 3t, and z equals 3 plus 3t. Now, a question might arise, and usually does when this is done in a live class, is I would get, it appears that we would get an entirely separate line by using the initial point as P2. That looks to be the case. Okay, well, we'll figure that out. So if I used P2 as my initial point, my parametric equations wouldn't start with 1, 2, and 3. They'd start with 4, 5, and 6. The direction vector is still the same. I claim these are the same line. These two sets of equations represent the same line. Okay, it's just that the lines are at different points. They trace out different points at different times t. If you miss that, in the first set of equations here, imagine letting t equal 0. You get the point 1, 2, 3. So when t equals 0, I get 1, 2, 3. So t equals 0, I get x equals 1, y equals 2, z equals 3. I claim that the point 1, 2, 3 is also on the second line. how can I get the x value to equal 1? I'd have to let t equal what? And in the second line. So I'm looking at the second line. 4 plus 3t is 1, so t needs to be -1. So if t equals -1, in the second representation, I get 4 minus 3, 1, 5 minus 3, 2, and 6 minus 3, 3. So in terms of our interpretation of this variable t as time, the t in the first line and t in the second line represent different times, or they could represent the same time. It's just the line traces out different points at different values of t. So at t equals 0, we get when time equals 0 on the first line, we're at 1, 2, 3, but it's 1 hour ago, t equals -1 on the second set of equations, that we're at the point 1, 2, 3. Okay, I hope that didn't confuse things too much. Okay, let's take a look at another example. For example, in algebra, one of the first things you did with lines as an exercise is to determine whether they were parallel or not. And that's what I would like to do in this example. So are the lines parallel? I'm going to give two equations, two separate sets of equations. Let's say line 1 has equations x equals 2 minus 3t, y equals -7 take away t, and z equals 4 plus 2t. So here's the first line. The second line, L2, is given parametrically by x equals 3 minus t, y equals 5 take away 2t, and z equals 1 plus t. Okay. Well, if we were in an Algebra 1 or even a pre-calculus setting, to determine whether two lines were parallel in R2, we would look at their slopes. If their slopes were the same, then remember the slope gives you the steepness. If the slopes were the same, then we have parallel lines. Well, we don't have slopes anymore. We have direction vectors. So we're going to replace the concept of slope with, or looking at the slopes to determine whether lines are parallel, to looking at direction vectors. So on the first line, we have, let's say, the direction vector v1 is given component-wise by -3, -1, and 2. I'm picking off the A, the B, and the C for the direction vector for line 1. Okay, I'm going to do the same thing for line 2. That line 2 has direction vector -1, -2, and +1. How can I determine if these two vectors are parallel? Well, you can get real fancy, and you can use the cross product. Remember the cross product, if the cross product is 0 and the vectors are non-zero, if the cross product is 0, the vectors are parallel. Not the dot product, the cross product. A much simpler way to determine if two vectors are parallel. Okay, so let's take a look at that in general. Suppose I have this vector, and let's say this is the vector, let's say that this is the vector u. And let's say we have the vector v is this vector. These two vectors are, in fact, parallel. If you place them on lines, these two lines would be parallel. Now it looks like the way I've drawn them that u is twice as long as v, but points in the opposite direction. Okay, so it looks like, the way I've drawn this, it looks like that u is equal to -2v, and that's how you determine if you have parallel. If two vectors are parallel, if one is a scalar multiple of the other. So that's the bottom line here. So vectors u and v are parallel if one is some scalar, non-zero scalar multiple of the other. Okay, so back to our vectors. Back to our vectors v1 and v2. These two vectors are not parallel. These two vectors are not parallel. In order to be parallel, we would need to just look at the first components. Just isolate in your mind right now the first components. Okay, in order to get that -1 to equal -3, I'm going to have to multiply -1 by 3. So I'm going to have 3v2 equals v1, but when I multiply the second and third components, they don't match up with v1. Okay, so if they were parallel, I would need to have v1 equals 3v2. But when you take 3 times the second and third components of v2, you don't get the second and third components of v1. So since v1 is not equal to some scalar multiple of v2, the direction vectors are not parallel. The direction vectors are not parallel. So the lines aren't parallel. So the lines are not parallel. The lines are not parallel. Okay, so the bottom line is very simple. I really went on about this because I kind of had to define to you what it means, or how you determine two vectors are parallel. And basically, to determine if two lines are parallel in 3 space, you take the direction vectors, and if one is a scalar multiple of the other, then they're parallel. If the one is not a scalar multiple of the other, then they're not parallel. Okay, well, we want to do some more with these lines. These lines are not parallel. Okay, now I want you to think about these two lines as giving the flight paths of two separate airplanes. So L1 is the flight path of plane 1, and L2 is the path of the second plane. Okay, and they're flying in the sky on a plane. Okay, well, maybe not one plane. They're flying in the sky. Now, what I just said about maybe not one plane is going to give away what I'm aiming for now. These lines are not parallel. If they were in R2, if they were in the XY plane and they weren't parallel, what would they do automatically? They would intersect. In the XY plane, if two lines aren't parallel, they're going to intersect. Either they're going to lie one on top of each other and intersect everywhere on the common line, or they're going to intersect at a point. Now, does the same thing hold true automatically in 3 space? If two planes are parallel, are not parallel, must they intersect? Absolutely not. Absolutely not. You can have the flight paths of the two airplanes not parallel, but they certainly don't have to intersect. One of the planes could be at an altitude higher than the other. Okay, so if lines that are parallel are not parallel and they don't intersect, if lines are not parallel, and this can only happen in 3 space, if lines are not parallel and they also don't intersect, they're called skew. S-K-E-W. S-K-E-W. So before we get to the actual example that I'm heading for, skew lines. Skew lines. They are lines that are not parallel and do not or don't intersect. So the next question is, do lines L1 and L2 intersect? Okay. Well, there's a common mistake that's made in trying to determine whether the lines intersect or not. Very commonly, students will take the equations for these lines, the parametric representations of these lines, and they set the x's, the y's, the z's equal to each other. And if you get a unique time, if you get one time that satisfies all three equations, then the student will commonly, and this is incorrect, assume that the lines intersect. Okay, if you didn't catch what I said, let me say it again. So here are two sets of equations for lines. It's common for students to do this. And so I'm gonna write this as wrong. To determine if these lines intersect, it's absolutely wrong to assume that, for example, 2 minus 3t needs to equal 3 minus t. And the reason why this is incorrect can be seen if you think back at t as representing time. Well, if I set 2 minus 3t, the x value on one line, equal to 3 minus t, the x value in the other time, and I'm trying to solve for time, I'm assuming that the two flight paths of the airplanes would cross at the same time. This doesn't have to be true. This doesn't have to be true. Flight paths of airplanes intersect all the time, but they don't do that. They don't intersect at the same time value. If they did, the planes would collide. So in determining whether two lines intersect, we have to assume that there's going to be if there's going to be an intersection, it has to be at separate times. So if you miss that, it's no big deal. So here's a representation of what's going on. If this, suppose the lines intersect. So here's line L1, here's line L2. And suppose they intersect at the point, I don't know, alpha, beta, and gamma. Okay. Now, the alpha, the beta, and the gamma, the x, the y, and the z for both lines are going to be the same, but they could occur at very, very different times. So they could occur at time equals, let's say, S is in Sam for line 1. So they could occur, it would occur where the x coordinate is 2 minus 3s. The y coordinate is negative 7 minus s. And the z coordinate gamma, strange looking gamma, equals, let's see, what is the z coordinate? 4 plus 2s. And that same alpha, x, that same beta for y, and the same gamma for z could occur at some time t on the second line. 3 minus t, 5 minus 2t, and 1 plus t for the z component on the second line. Okay. So in these cases, we would set the x, y, and z components or coordinates equal to each other. So in this case, 2 minus 3s will equal 3 minus t. S and t could be very different. Negative 7 minus s equals 5 minus 2t. My s's and 5's look very similar. Sorry about that. 4 plus 2 times s equals 1 plus t. And these three equations need to be solved for both s and t. Now we have three equations and we have only two unknowns. So the way we're going to solve this as a system of equations is by looking at two equations at a time. Okay, so let's consider the two equations, 2 minus 3s equals 3 minus t, and negative 7 minus s equals 5 minus 2t. And let's see if we can solve for s and t. If we do get a solution for s and t, then the answer will be that the lines do intersect, as long as when I substitute those values for s and t into the z-coordinates, I get the same thing. If you missed that, we'll come back to it. Let's try to solve for s and t. Okay, so what I'm going to do is I'm going to simplify the system a little bit. So let's go this way. I'm going to simplify the system a little bit. I'm going to write the first equation is 3s minus t equals negative 1. And the second equation, let's say as s minus 2t equals negative 12, I think. And I'm going to solve this system for s and t. Now, at this point, you have several methods for solving systems. I think what I'll do is I'll take the second equation and maybe multiply it by negative 3 and then add the two equations together. You can use whatever method you're comfortable with. So if I do that, so I'm going to come down now, and I'm going to get 3s minus t equals negative 1, multiplying the second equation by negative 3s plus 6t. If you want to do a different method, you can stop the video and do it on your own if you want, or you can just continue on. Now I'm going to add these two equations together. S's cancel, whole idea. So 5t equals 35. So t equals 7. So if these two lines are going to intersect at a particular time, it's going to be at time t equals 7 minutes, hours, whatever on the second line. And to get the time on the other line 1, I'm going to substitute t equals 7 into either equation with s, any of the equations with s and t. So I have an equation 3s minus t equals negative 1 from above, and I'll substitute t equals 7. So if I substitute t equals 7, I get 3s minus 7 equals negative 1. 3s equals 6 if I add 7 to both sides. So s, ugly looking s, not getting any better, s equals 2. So the x and the y coordinates meet, they match up on the first line when s equals 2 and on the second line when t equals 7. But we have one set of coordinates left to worry about. We have the z-coordinates. We have the z-coordinates. One of the z-coordinates is 4 plus 2s. The other z-coordinate is 1 plus t. I need both of those to be equal. Okay, I know that the x and the y on the two flight paths of these airplanes, they match up, but they could match up at different altitudes, at different z values. So I'm going to substitute s equals 2 to get 8. So the z value is 8 on the first line, and on the second line, the z value is 1 plus t, which is 8. So these are equal. The z values are equal. The third set of equations match up. So the lines intersect. So the lines intersect. If these were airplanes, the flight paths cross. The two flight paths cross, but at different whats? At two very different times. At 2 hours on one and at 7 hours on the other. Okay. So what would happen if they intersected at the same time? What would you say about these two airplanes? We would say that the two airplanes collided. Okay. So it's nice when we have the lines intersecting but at different times. So these lines are not skew. They are not skew. They are not parallel, but they do in fact intersect. Okay. Now, before we move on to the second topic in this section, planes, I want to look at a third way of representing lines in 3 space. So just as a quick recap, lines, vector equation can be used, a vector equation could be used, R equals R naught plus TV, where R naught is an initial position vector and V is a direction vector. You can give parametric equations. That means you're given the equations of the lines coordinate-wise. X equals x naught plus at, y equals y naught plus bt, and z equals z naught plus ct. But there's another way to do this, and it's not as popular as the first 2 ways. These first 2 ways are very popular, with the second way being the most popular. Parametric equations are very, very common. So the last thing to do the last way to write these or to represent a line is to take the parametric equations and solve each of them for t. If you solve each of the parametric equations for t, you get t equals x minus x naught over a. There's no magic there. I just subtracted x naught from both sides and then divided by a. You could also get y minus y naught over b. And you could also get z minus z naught over c. Now, since all 3 of these equal t, then we can eliminate the parameter. I never identified that t as with the word parameter, but that's what it's called. Don't worry about it if you missed it. This is a way of writing representing a line. I said this, I didn't say this equation, because this is really 3 different equations all together. You have one equation representing x's and y's, or you have an equation that that gives you a representation or a relationship between y's and z's. And you also have, if you set the third expression equal to the last expression, or first expression equal to the third expression, you get a third equation. So all 3 equations simultaneously give you an equation, a representation for a line. These are called symmetric equations. These are called symmetric equations. Symmetric equations. So we can represent lines by what are called symmetric equations, by giving parametric equations, or by giving a vector equation. So one real quick example of symmetric equations. So find symmetric equations for the line given by x equals -3 take away t, y equals 3t, z equals 4 plus 2t. It's not difficult. It's not difficult at all. Okay, it's x minus x naught, x minus -3 over a -1, y minus y naught, so y minus 0 or y over b equals z minus 4 over, which is z naught, over c, the third component of the direction vector. Okay. Well, let's move on to planes. Let's move on to equations of planes, the second topic for our section. Okay, so let's start considering planes by answering the question. First, we'll answer a question about lines. We've already answered the question actually in the last hour, but let's take a look at it again. Can a line be determined by knowing a point on the line in a direction parallel to the line? Of course. That's how we found the vector form of a line. So yeah, if we know a point in a direction, it's like knowing a point in a slope in R2, we can find the equation of the line. Now here's the similar question. Can a plane be determined with the same two bits of information? If I know a point and a vector parallel to the plane, can I completely determine the plane? The answer is no. So here's a plane. Here's the reasoning. Here's a plane. Suppose I know a point. Here's a point right here, a plane, and I know a vector in the plane. Any vector in the plane will be parallel to the plane. So I know a point and some, let's say, red vector in the plane. Right there. Is that the only plane that contains that black dot right there and that red arrow? And the answer is no. No, 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 no. Okay, I'm going to draw another plane with the same two bits of information. Okay, so here's our plane, another plane with the same two pieces of information. The green plane that I'm drawing also contains the red vector and the black dot. Okay, so in fact, there are an infinite number of planes that contain one vector and a single dot. So there's no way to identify a single plane by knowing a point in the plane and a vector in the plane. Okay, so can I find the equation of a plane if I've given a point in the plane and a normal vector, a vector perpendicular to the plane? So what if I'm given a point, oops, that third line didn't work out real well. What if I'm given a point, there we are, thick heavy black dot there, and I'm also given a vector that's perpendicular to the plane. Say this red vector right here, perpendicular to the plane. Can I completely, does that completely define the plane? Is there only one plane that satisfies those two things? Yes, of course. Of course. This vector is perpendicular to the plane. So if you tilt the plane in any other direction, you're going to change the direction of the normal to the plane. Well, you might think, well, there's also another normal direction downward. That's okay. That's okay. The downward normal direction would also determine the same plane. My point is, if I'm given one of those two red vectors, either the one that goes up or the one that goes down in a point, is there only one plane that passes through that point and has either of those upward or downward directions? The answer is yes. Okay, so that's going to be the given information to be able to find the equation of a plane. Given a point in the plane and a normal. So given the point in the plane and a normal direction, a normal vector to the plane, find the equation of the plane. That's our task now. Let's take a look at how that works. Really, the geometry is kind of neat. So here's our plane. I'm drawing it horizontal just because it's convenient for me to do that. And here's a picture of the first octant. Remember, the first octant is that part of 3 space where all 3 coordinates are positive. And here is the point x naught, y naught, z naught, right here. Here's the point x naught, y naught, z naught. Okay, what I can do, just like I did with the line, is I could draw a position vector to the point from the origin up to the point, and I can call that position vector R naught. And at the point XYZ, I'm going to put in or draw in the normal vector, and I'm going to draw it green. If my surface will allow me to, I'm going to draw it green. So here's the normal vector drawn at the point P. Okay, then I'm going to select an arbitrary other point on the line. I'm going to draw a different point on the line other than x naught, y naught, z naught. I'm going to draw it right there. It's some point, a variable point, if you will, x, y, z. Okay, then I'm going to draw a position vector to that point. Okay, and I'm going to do it in red again here. So here's a position vector to that point. Okay, I'm going to call that position vector R. Now I'm going to draw in a displacement vector from R naught to R. Okay, and that displacement vector is nothing more than R minus R naught. Okay, remember, if you want to find the vector R minus R naught, you draw it from the tip of R naught to the tip of R when R and R naught are drawn tail to tail. Okay, just from our earlier lecture. Now notice that displacement vector is always going to be perpendicular to my normal vector. That displacement vector is going to move around as x, y, and z moves around the plane. Remember, x, y, z is variable, but it's always going to be perpendicular. It's always going to be orthogonal to n. So it's always going to be the case that n, if two vectors are perpendicular, say non-zero vectors are perpendicular, what happens? What is their dot product? Their dot product needs to be 0. The scalar product or dot product of two orthogonal vectors is 0. That right there, that's the vector equation of a plane. This is a vector equation of a plane. Okay, it looks a little abstract written like that. Let's put the numbers in. Let's put the quantities in. The normal vector, did I identify? Yeah, I did. I identified it as A, B, C. The normal vector is a vector whose components are A, B, and C. I'm assuming that the position vector has components x, y, z, and R naught, x naught, y naught, z naught. So when you subtract them, the components of the resulting vector are x minus x naught, y minus y naught, z minus z naught. That is also the vector equation of the same plane. It's just written with all the components intact. Let's take that dot product. Let's find that actual dot product. We get A times x minus x naught plus B times y minus y naught plus C times z minus z naught. And this is a very popular form of the equation of a plane. This is the scalar equation of a plane. Okay. Planes are easier to describe than lines. Lines, they took up a lot of real estate in this video segment because we had vector equation, parametric equations, and symmetric equations, and then we had to take that side trip of skew lines and so forth. That was a lot of work. Planes are a little easier to describe. Now in your homework, some of the questions involving planes or the opposite. They're really involved. So plan on spending some quality time. I think it's like around the 30s in the homework where I think where it gets kind of involved. The geometry gets involved. Okay. So let's do a simple example. Find an equation. Find an equation of the plane passing through, so passes through the point -1, 3, 4, perpendicular to let's say normal vector n equals 4, -3, 1. Okay. This is very, very simple. We're given everything we need to do this. Super simple. Here's just geometrically real quick what's going on here. We have a point -1, 3, 4, and we're given a normal vector to the plane. And that's all we need to be able to find the equation of a plane. And by an equation of a plane, let's say I want the scalar equation, just for the heck of it. The scalar equation has a times x minus x naught. A is the first component of your normal, plus b times y minus y naught, plus c times z minus z naught equals 0. So a is 4 x minus x naught is -1, plus b is -3, so I guess I should put in a minus 3 times y minus 3 plus 1, third component of normal is 1, times z minus 4 equals 0. Okay. So let's distribute and simplify stuff. So we get 4x, just the variables first, minus 3y plus z. Then I'm going to get 4 by distributing the 4 into the first set of parentheses, plus 9, which is 13, minus 4 is plus 9, equals 0. Okay. This is called a linear equation. Linear equation. It's what half of our flagship math course, our Math 250 course at Cerritos, it's what half of the semester is basically based on as equations of this. It's called a linear equation. Even though it's an equation of a plane, it's called a linear equation. Okay, so linear equations are any equations of the form ax plus by plus cz plus d equals 0. These are all examples of linear equations. And linear algebra deals with, to a great extent, equations that look like linear equations. Let's take a look at an example. Let's look at an example. So for example, find an equation. Find an equation of the plane passing through 3 points, P, 3, 0, 1, Q, -1, 2, 3, and R, -2, -2, -1, and +4. A little sloppy there. Okay. Well, to find an equation of a plane, we need 2 things. A point in the plane. Well, we have overkill. We have 3 points. So we have more than we need for the point. But we also need a normal. We need a point, and we need a normal. We have 3 points, but no normal. How can we find a normal vector if we know 3 points? If I know a point P, I know a point Q, and I know a point R, first of all, do 3 points determine a plane? Absolutely. 3 points that are not collinear. 3 points, non-collinear points, to definitely determine a plane. What am I talking about? Well, can I form a tabletop by knowing where 3 marbles are on the tabletop? Of course. Okay. Only one plane can contain those 3 marbles. Only one tabletop can contain 3 marbles whose location is given. So how do I find the normal? How do I find the normal vector? Well, I can find a vector PQ, displacement vector. And I can find a displacement vector PR. Neither of those vectors will be normal to the plane. They both lie in the plane. Now, here's the question. How can I find a vector perpendicular to both PQ and PR? And the answer is, if you didn't think of it, just take the cross product. Take PQ cross PR or PR cross PQ, makes no difference. If I take PQ cross PR, I'm going to get a vector that, according to my drawing, will have to point downward, because why? Why doesn't it point up? Because of the right-hand rule. But that vector is going to be perpendicular to both planes, because the cross product is in fact perpendicular to both vectors. PQ cross PR will be a perfect choice for my normal vector. So, a little work to do. Displacement vector PQ is, to get the displacement vector from P to Q, I subtract the coordinates in reverse order from Q to P. So -1 take away 3 is -4. 2 take away 0 is 2. I'm subtracting the y coordinates. Now subtract the z coordinates with P and Q. You get 3 minus 1 is 2. Okay, so what about PR? Same difference. PR is subtract the x coordinates, the x coordinate r minus x coordinate of P. -2 take away 3 is -5. -1 take away 0 is -1. And 4 take away 1 is 3. So there are PQ and PR. So my normal vector I'm going to choose as PQ cross PR. And that's nothing more than the symbolic determinant with I, J, and K across the first row. Standard basis vectors I, J, and K. Components of P, -4, 2, and 2. The components of Q, -5, -1, and 3. Then I compute this cross product. Okay, so if I cover the first row, I'm going to have a determinant that's left. 2 times 3 is 6, minus -1 times 2. That's 8. You can slow the video down or stop it to confirm if you want. Then I cover the second column and take the determinant of the numbers that remain. So -4 times 3 is -12. Take away -5 times 2, so plus 10. -12 plus 10 is 2. But remember, -2, but we changed the sign of the middle component on the cross. Okay, again, you can stop the video and do the cross product on your own if you want, if this is too fast. Cover up the third column. Determinant of the remaining numbers is -4 times -1 is 4. take away negative 5 times 2, so plus 10. So 4 plus 10 is 14. That's a perfectly good normal vector. Now, I'm going to do something a little tricky here. I could also choose something a little simpler. Instead of 8, 2, and 14, I can choose 4, 1, and 7. Why? Why can I do that? Because 8, 2, the vector whose components are 8, 2, and 14 can be written as 2 times the vector whose components are 4, 1, and 7. I can basically factor out a 2. And if 8, 2, 14 is a scalar multiple 2 times 4, 1, and 7, that means those two vectors are parallel. 8, 2, and 14, that vector whose components are those numbers, is parallel to the vector 4, 1, 7, because it's a scalar multiple of a vector whose components are 4, 1, 7. Okay. So finally, the equation of the plane then is 4, the first component of the normal vector, times x minus x naught. X naught can be, the x naught, y naught, z naught can be chosen either as the components of p, q, or r. We have 3 points. There's a 0 in p, so I think I'll choose 3, 0, 1. So 4 times x minus 3 plus 1 times y minus 0 plus 7 times z minus 1 equals 0. Or I can write this as 4x plus y plus 7z, or let's see, also minus 12 distribution, minus 7 more, minus 19 equals 0. And that would be a perfectly legitimate linear equation for our plane. Okay, so here's our last example. It's a simple one. We've been here for a while. Let's take a look at a simple last example. I want to determine whether two planes are parallel. Determine whether the following planes are parallel. Okay, so I have 2x minus 3y plus 4z equals 7. I also have as my second plane negative 6x plus 9y minus 12z equals 0. 2 planes. How can I determine if they're parallel? We'll say I'll call the first one plane 1, the second one plane 2. So how can I determine if plane 1 and plane 2 are parallel? The answer is compare their normals. If the normal from one plane is parallel to the normal from the other plane, then the two planes must be parallel. Okay, so just find two normals. The first normal, the normals are the coefficients of the variables, the components of the normals. So the components of n1 for plane 1 would be 2, negative 3, and 4 respectively. The components for the second normal, just pick off the coefficients of x, y, and z are negative 6, 9, and negative 12. So let's see, are these two vectors parallel? Well, just look at the first components. In order to get 2, and in order to turn that 2 by multiplication into 6, I need to multiply by 3. So let's see what 3 times n1 turns out to be. 3 times n1 turns out to be 3 times 2. Oh, let's say negative 3 times n1. Negative 3 times 2 is negative 6. Negative 3 times negative 3 is 9. Negative 3 times 4 is negative 12. And that is exactly n2. N1 and N2 are parallel. N1 and N2 are parallel. That means the normals are parallel. So the two planes are parallel. Planes are parallel. Okay. There's one thing we didn't cover in the video lecture. It involves the distance from a point to a plane. I'm leaving that for you to look at in your textbook. So I think there's at least one homework problem on it. It's a very simple item, but I want you to look it up. So from section 12.5, remember you're supposed to read the text, all the text, but in particular, read for yourself about the formula for the distance between a point and a plane. And that finishes up section 12.5. So go ahead and dig into homework as soon as you get a chance. And as always, I'm looking forward to talking with you all again soon.